hear what you have to say.
All right, great. Thank you, Xander. And just to confirm, you can hear me all right over there?
I can, yes. Thanks for
Okay.
we hear you loud and clear, and I can see your presentation, so I think you're all set.
All right, great. Well, yeah, thanks everybody for giving me this opportunity to present some of this work that I did during my master's here at NAU. I think as a grad student, it's kind of like your worst fear to do all this work and have it get shoved away in a drawer somewhere and never see the light of day. But this is a really good opportunity for me to show some of this stuff. So thank you. So just kind of a quick preview here on the intro slide. So those three images that you see in the middle of the screen are actually all taken in the exact same location in the study area and just kind of represent the different types of ways to look at the same thing here. Okay, so the motivation behind this research came kind of having to do with all these large wildfires that we see across the West, and the land manager's response being the fuel reduction treatments to help kind of mitigate these. But I was looking at the monitoring plan for a fuel reduction project just outside of Flagstaff, and this question stood out to me, which was, did the investment effectively reduce the risk of catastrophic fire? And so I started thinking, how do you even get at answering this question? And how do you measure risk of catastrophic fire? And so that sent me down the road of fire behavior modeling. So in fire behavior modeling, it's important to first talk about LANDFIRE data, which is commonly used to do this sort of thing. So LANDFIRE is a federal program. It primarily uses Landsat satellite imagery, and it's available for free to the public. The data is in 30-meter spatial resolution, and the temporal resolution, or kind of the frequency at which this data becomes available, is every 2 to 5 years. And so the product that we used from LANDFIRE was the fuels data. And so this fuels product includes canopy cover, which is the percent of canopy within a 30-meter cell, canopy height, which is the average tree height within that 30-meter cell, and then canopy base height, which is the average height of the bottom of the canopy bulk density, which is the density of the canopy, topography is elevation, slope, and aspect, and then fuel model, which is the type of material that's found within that area, being timber or grass, etc. And so LANDFIRE data is what people mostly use to model fire behavior. And so with those fuels products that I just mentioned, you take those out of the database and you create what I like to call this raster sandwich. And so this raster sandwich goes into the software. In this case, we used FlamMap, and the output becomes like what you see on the right there. And so what this is saying, this is a map, and it in the blue areas indicate areas that are modeled for surface fire, and yellow areas are passive crown fire, and red areas are active crown fire. And so this is one way that you can sort of indirectly get at what the fire risk is for an area. So general questions that we wanted to answer were, can you use UAV surveys to estimate these canopy fuels? And then can you take it a step further and use those measurements to model the potential for crown fire? And then we also wanted to see how these different data sources compared when you model the fire behavior, being LANDFIRE versus UAV. And some more specific questions we wanted to get at were, can you use the UAV to estimate canopy cover? And then can you delineate individual trees, which effectively gives you a measure of tree density? And then can you take these individual trees and measure their tree height, the canopy base height, and their bulk density? And so I'll be talking about different data sources. And so I just wanted to kind of quickly mention what these are, some examples of these. So first is satellite imagery. There's all different kinds of satellite data, but most commonly used is Landsat. So Landsat is 30-meter resolution, and the great part about this is that it's free. And next you have aerial imagery, or imagery that's taken from an airplane. And in this case, this is an example from NAPE imagery, which is 1 meter resolution and is also available for free. And so these different examples here are showing an exact same area so that you can kind of compare them all to each other. And third, you have UAV imagery. And so this is an example of some of our UAV imagery that's in 15 centimeter resolution. And so you can see that there's definitely more detail when you zoom in there. But it comes at a little bit of a cost compared to the other two free products. And then I'll just mention LiDAR. We didn't actually use LiDAR for this, but it's becoming more popular. So I just wanted to throw this in here. LiDAR is really good at giving you really nice, crisp, three-dimensional data, but it definitely comes at its own cost. So our study site was located just outside of Flagstaff. That orange rectangle and the pink rectangle are two different flight areas. And combined, this made up just over 12 hectares, or about 30 acres. It's primarily ponderosa pine forest. It's definitely within the WUI of Flagstaff. It's in really short distance to the closest houses right there. And I should also mention that it's part of the Flagstaff Watershed Protection Project, which is that local fuel reduction project that I mentioned. And interestingly, this spot right here was actually thinned since we did this project. So that would be a cool opportunity to go back there and do a similar analysis post-treatment. So the UAV or drone that we used is called an EB, and it's a fixed wing UAV. It's more of an airplane style rather than a helicopter style. And the sensor on board was a multispectral sensor. And so this captures images in 4 different bands. These bands are a little bit different compared to the visible wavelengths, or like a photo taken from our like a camera phone or something. And this is more geared towards looking at vegetation and vegetation health in particular. So our UAV survey did a grid pattern over that orange polygon. And in this grid pattern, it had 85 to 90% image overlap between the different images that it took. The max flight altitude that we set for this was 120 meters, which is just below that 500 or 400 foot legal limit. For this flight here, the duration was 22 minutes, and it covered just about 15 acres. And these white points that are on it now represent each photo location. And there are 960 images that were acquired in this flight total. So with that UAV imagery, we created 2 different products that we used. First is the ortho mosaic. And so what this is it's just a combination of those 960 images that are stitched together, and it basically makes an aerial photo of the area. And so this is that 15 centimeter resolution, and includes all 4 bands that were captured by the sensor. And here's an example of what some of that imagery looks like, kind of zoomed in a bit. So next is a 3D product called a point cloud. And in order to create the point cloud, we used a process called structure from motion. Now what this does is it takes different image perspectives. So in this example right here, if you consider each red point to be a photo location looking down at those trees, now you have 6 different perspectives of those same trees. And so the structure from motion software is able to use those different perspectives and create a 3D model of what that would look like. And so here's just an example of one of our point clouds from one of those flight areas. And you can see here that the trees were reconstructed in 3D. And just for reference, this point cloud here has just over 5 million points. So next in our study, we also included some field data. And this was mostly for validation purposes. We wanted to compare some of our UAV field or UAV measurements to the field data to see how good they were. In our field sampling, we did this in a 10 by 10 grid, and we picked 57 random plots across this grid. And this included 7 different density classes because we wanted to include a variety of different density classes from 1 tree per plot all the way up to 7 trees per plot. And in total, we measured 192 trees. And the measurements we took on each tree included its height, the base height, as well as the canopy diameters. So next we transition into estimating canopy cover. To do this, we first did this using the UAV data, but we also did it using 2 other remotely sensed data so that we had something to compare to using the UAV data. So here's an example of our canopy classification that we did with the UAV imagery. So this is in 15 centimeters, and the green pixels here indicate it's canopy, whereas black is non-canopy. Then we did the same thing using NAPE imagery. Now this is in a 1 meter resolution. And then we also used a data set from Zachman and Dixon. And this is a data set where they used similar aerial photography to NAPE, but it was a higher grade photography. So it was in a higher resolution. And so their product was in a 30 centimeter resolution. So then we took that canopy classification and turned it into a canopy cover percent estimate. And so we took what you see on the right there, the green areas of canopy, and turned it into 10 by 10 squares. And so each 10 by 10 square here represents the number or the amount of green pixels within it. And so that's effectively the canopy cover percentage within that area. And then we stacked these on top of each other, the UAV and NAPE and the Zachman and Dixon, and compared them to each other. And we found that the UAV and NAPE were definitely similar. And the UAV and Zachman and Dixon were actually even more similar. So next we jump into the individual tree delineation. And so for this, you go from the image that you see on the left, where it's just a point cloud with your trees in it, and you delineate the individual trees out of it. So on the right, each one of those different colors represent a different tree. Now this step is needed in order to make individual tree measurements, but also to estimate the tree density, because then now you have the number of trees for a specific area. So after we did this, we did an accuracy assessment, and we wanted to see how good we were at delineating the trees versus the GPS locations of those trees that we found in the field. And so during this accuracy assessment, 3 things can happen. So you have a true positive, an omission, or a commission. So true positive is a 1-to-1 match. So in this example here, the green points represent the GPS field locations of those trees. And the pink points are what we found or what we delineated from the UAV point cloud. And so we found 2 trees, and there were 2 trees in the field. Next, you have the omission. And so there are 2 trees in the field, but we only found 1. And then the commission, where there's 2 trees in the field, but we actually found 3 from the UAV. And through several trials of this, the best that we could actually do here, we could find 74% of the trees using the UAV data. That's 74% of the trees that we measured in the field. And we also had a 16% commission, so that's 16% extra trees. So another thing, we wanted to take this a little step further and see if the density of the plot affected our ability to find trees within it. And so on the x-axis here, on the bottom is the density class, or the number of trees within that plot. And then the y-axis is the number of trees that we delineated from the UAV data. And so I've also included trees per acre in green there, which is a little bit more relatable as far as tree density goes. But to kind of walk through this graph here, so for 1 tree for a one tree plot, we're usually able to find one tree from the UAV data. From a two tree plot, we can usually find two, and three for three. But the interesting thing here, and the main takeaway, I think, is that when you get into the 4, 5, 6, and 7, that they all start to kind of blend together. And so what this was telling me is that when you get into kind of those more dense areas, and I understand in some part of the country, or some parts of the country, that this might not actually be that dense, but above 160 trees per acre, it becomes pretty hard to parse out those trees from the point cloud. But below that, it seems to do decently. So next, we wanted to compare the tree heights from the UAV data to those we measured in the field. Now, this is for the trees that we were able to successfully find in the point cloud. And when we compared those heights with the field heights here on the x-axis and the UAV heights on the left or on the y-axis, we can see that they're pretty well correlated. Another interesting thing about tree heights here is that we learned the Forest Service acceptable error for measuring tree heights in the field. Now, this comes from the FIA protocol, and their protocol is less than 20% error in height measurement 90% of the time. And so we wanted to see kind of how we stacked up to that using the UAV-derived heights. And we found that on average, we had a 5.3% error 90% of the time. So for the trees that you can successfully find, it does actually measure their height decently well. Okay, so next we jump into canopy base height. And to do this, we tried using the point cloud height percentiles. And so that image on the right there is a side profile point cloud of a single tree. And so the height percentile, the 5th percentile here, means that 5% of the points are below that height. 10th percentile means that 10% of the points are below that height. And we found that the 5th percentile was the best relationship to our field measured base heights, but it was actually a relatively weak relationship. And then next, we tried all sorts of different methods to estimate canopy bulk density. But long story short, in the end, we couldn't really find any good way to do this that would correlate to what our field measurement estimates would say. So why did we try to measure all these? Kind of just bringing this back. These are all the canopy fuels estimates that go into modeling crown fire. And so in the most basic sense, these variables help determine whether you have a surface fire like you see on the left or a crown fire like you see on the right. So the last step that we tried was modeling crown fire behavior using the UAV data. And now this was kind of more of a trial just to see if it could be possible and to see what the outputs would look like. So the different UAV data that we plugged into the raster sandwich here was the topography, the elevation, slope, and aspect, canopy cover, canopy height, canopy base height. But canopy bulk density and fuel model, we actually didn't measure using the UAV, so we didn't include that. So the outputs from the FlamMap fire models. So in this first column here for LANDFIRE, this is using just LANDFIRE data. The output said that there was 0% surface fire, 14% passive crown, and 86% active crown. But when we threw everything that we had from the UAV into the model, it was drastically different with 100% surface fire. Canopy base height seemed to be the major player in that, when we included just canopy base height from UAV, it was 98% surface fire. So the main takeaway here is that it is possible to use FlamMap with UAV data, but it produces very different results. And we found the canopy base height was the biggest driver in that. So implications, overall UAV data can be used to estimate some canopy fuels, I would say. mostly canopy cover. It's pretty good at that. It's comparable to the other data sources. Tree density, if your area is not too dense, it would actually be pretty decent for this. And in the same case for tree heights, if you can find those trees, then it can measure their heights pretty well. Canopy base height and canopy bulk density definitely could use some improvement here. As far as the crown fire modeling goes, we found that different data sources can definitely lead to very different estimates of crown fire. And the current data sources in our research, we found they can have highly variable accuracies depending on where you're found across the country. And you definitely need to consider the accuracies of each of these inputs as you use them. And it's also important to supplement LANDFIRE and not just take it for what it is. And typically people do this with field data as well as expert knowledge for the area. But I think UAVs also kind of open up a new opportunity to try to do this. All right, and that's all I got. And feel free to reach out to me via email if you have any questions further than what you have here. So yeah, thank you.
Thank you so much, Patrick. That was a great presentation. Really interesting to think how far we've come. A couple questions came in the chat window. We'll address maybe the 3 or 4 that came in, and then we'll jump over to our next presentation, and there'll be a little bit more time for discussion, questions, or answers at the end of both presentations. So I think the first question that came in was about the sensor on the UAV, and Christopher Roberts asked whether you're using Red Edge or Tetracam.
I'm not too familiar with what the Tetracam is, but this camera included, or the bands included on that sensor were the red, red edge, green, and near infrared.
And do you don't happen to know the manufacturer or the brand of the camera, do you?
Oh yeah, I do. So that it's called the multispec 4C.
Okay.
And so you could look that up and find different specs on that sensor. I will also mention that the equipment that you use, both that we use, the platform and the sensor, this was a few years ago, and I think this technology is evolving so fast that there's already newer versions of both of those that are more capable than what we use. So yeah.
Okay. Yeah, it's hard to keep track of all this stuff. Similarly, Kevin had a question about how you did the image classification and whether you used RoboSect or not.
Oh, I don't think I'm too familiar with the RoboSect, but is he referring to the canopy cover classification?
Yes, I think that's the disadvantage of doing questions at the end here. Yes, basically canopy versus non-canopy, yeah.
Yeah, so actually I have here's another slide here. So we took the orthomosaic that you see here, and we used NDVI to classify areas of canopy, and actually combined NDVI with the clustering threshold. So it had to have a cluster size of a certain number of pixels in order to be classified as a canopy. And after that, we actually overlaid the digital surface model on top of that to rule out any areas that said it was canopy, but that had a really low, actually a height of below breast height. Because we weren't interested in any of the shrubs or the grass. We wanted to just find tree canopies above breast height. And so including that kind of got rid of a lot of the noise out in the wide open.
Yeah, that's really interesting. Thank you. And another question, I guess this is, you sort of just addressed Jeremy's question. He asked if canopy cover was based only off only the ortho or incorporated any structural values like canopy height model. And that's like what you were just talking about, right?
Yeah, exactly. And yeah, we found that to be pretty effective because we did have a lot of just kind of noise points that were obviously not canopy areas. And we found that to be a pretty good way to rule out those. So.
Okay. We had another question about one of the benefits of having folks from other parts of the country highlighting our ponderosa pine forest have pretty minimal under or mid-story. And Kurt is wondering if you can just sort of speculate about how some of your techniques might work in forests with a more dense mid or understory. I mean, even say Gamble Oak, like if that, I don't know if you had any of that.
Yeah, I think, yeah, what we were just talking about before would definitely help rule out some of those things and classify between, you know, your trees as opposed to a shrub. But yeah, definitely if you include more understory, it gets more and more difficult. If you have different height classes and all that becomes more and more difficult to parse out. And so our area, I guess, relative to the scale of difficulty was probably on the end of easier, I would say.
Yeah. Yeah. A couple other questions I think we can address relatively quickly. Did you look, Patrick, at how the UAV-derived canopy cover, canopy height, canopy base height compared with the LANDFIRE estimates for the area?
Yeah, so I looked into that, just not really as part of this project, but more as personal interest. And it's hard to compare because it's not really apples to apples there, just resolution differences. But they're pretty different, even just when you combine our resolution to a 30-meter pixel and average it out, we found pretty different results.
Okay. Yeah.
But I would say, I mean, the general trend was similar. Like for canopy cover, for example, if you had areas of high canopy cover, they appeared high in both data sets, and low was low, but kind of that variation in between was a little bit different. Interesting.
Yeah, I think that sort of points to 10 years from now, we'll probably have a very different LANDFIRE data set, and maybe based on some of these new data collection techniques. Let's see, are your approaches for modeling canopy bulk density kind of talked about in the paper itself? Oops.
Oh, I think I lost you there for a second.
Oh, sorry. I was wondering, Gregory asked whether your modeling approaches for canopy bulk density are kind of detailed out in the paper.
Yeah, they're detailed out a bit more in the paper. Kind of in short, we use some allometric equations to go from height and diameter to mass. And then we used the canopy diameter to estimate a volume. And so having the mass and volume, we combined for density. And so we did that using our field data, and we tried to do the same process using the UAV data, but they didn't match up at all. And yeah.
Okay, great. And then the last question was about the NDVI, so that the cover map. Did you just use a simple NDVI threshold, or was it sort of a supervised classification to pull out that part of it?
So we just use, here's another slide kind of having to do with that. So we just use a simple NDVI calculation using the two different bands. And once we had that NDVI raster that you see here, we used a tool called the segmentation image tool. And so what this does is you set an NDVI threshold, but also that minimum cluster size that I mentioned. And so it has to meet that threshold and have neighbors of a certain amount that meet that threshold to be classified out.
Great. Well, we should change gears to our next topic. Patrick, thanks again for presenting. And first I should give Jim Higgins the controls so he can start sharing. Hang on one second. Okay. Okay, so Jim, you should have ability to share your presentation and unmute yourself, etc.
Okay.
And yeah, say that again.
I said I'm unmuted now.
Yep, you are, and we can hear you.
Okay.
And while Jim is getting his presentation set up, I'll go ahead and introduce him. Jim Higgins leads the engineering development at Drone Amplified, and he's going to talk about how UAS aerial ignition device that they've created called Ignis. Drone Amplified, if you're not familiar with it, is a company that it's a technology company focused on creating innovative tools to provide land and fire managers safe, more efficient, and more cost-effective solutions. And I'm really pleased to have Jim on today. He previously was research and development engineer at Pulse Aerospace, designing unmanned helicopters. And Drone Amplified and Jim are based in Lincoln, Nebraska. So it's, again, kind of cutting across regions here, and that's great. And so without further ado, Jim, I'll turn it over to you. And again, we'll do some questions and answers at the end. Thank you.
Okay. Xander, can you see the Ignis logo with flames in the background?
Yep, it's all working the way it should. Thank you.
All right, good deal. All right, well, I will jump in then. As Xander mentioned, my slide will advance. There we go. I'm Jim Higgins with Drone Amplified, and yeah, I'm excited to join you guys today. Thank you very much for having me. It's enjoyable to meet all you new people. I see a few familiar names here, but a lot of new ones too. So I'm just going to talk about our Ignis system we've created today. So I'm going to cover some motivation, development and capabilities, safety, the user interface, and then hopefully we'll have time for some questions. So motivation. I know that I'm preaching to the choir with this group, but managing fire puts people in danger, and it's costly. In the US alone, there's $60 billion a year spent in direct cost for managing wild and prescribed fires, and an additional $350 billion a year in damages caused. Sadly, the costs are not just monetary, though. Over the past 25 years, there's been an annual average of 17 firefighters killed while combating these fires, and that number appears to be increasing. So to help solve this problem, we've utilized the growing utility of drones, or UAVs, and created a cutting-edge, safe, and affordable aerial fire management tool that helps keep personnel out of harm's way. So the current solutions for fire management vary in their cost, risk, and functional capabilities. The chart here shows a graph that plots out a few common methods based on their risk and application. The drip torch over here in the lower left is useful for small flat areas and carries a relatively low risk. The ATV allows more area to be covered but can lend itself to riskier situations. And finally, in the upper right, manned helicopter aerial ignitions can ignite the largest and most complex areas, but they're also higher risk in terms of personnel and equipment costs. Our goal at Drone Amplified was to fill a void in this chart by providing a solution for larger, complex areas with a much lower associated risk. Now we hold no delusion that we're going to replace helicopters, because obviously helicopters can ignite much larger areas, but we wanted to fill a gap in this sort of functional chart. Now I'll talk about the development a little bit of the tool. So a brief pictographic history of Ignis is shown here. The first several versions were products of graduate research in the Nimbus lab at the University of Nebraska-Lincoln. The system has evolved over about 4 years from a proof of concept prototype to the commercial product it is today in the lower right-hand corner. The video on this next slide will give some details on how Ignis is made. This equipment is a technically advanced piece of robotics and automation. It was created using software simulation, computer-aided design, computer-aided manufacturing, and computer numerically controlled machining for the design and development. It is made from premium aerospace materials like carbon fiber composites and aircraft-grade aluminum. More traditional manufacturing is also required. Autonomous systems require significant electronic and sensor integration to monitor and control the various system processes. Ignis was engineered to be fully integrated with the UAV platform carrying it for a turnkey solution. Focusing on aerospace objectives drove part design to be light while maintaining strength and structural rigidity, and using a selective laser sintering process for some of these parts results in durable complex geometries at a much lower cost than through traditional machining techniques. The software designed to control Ignis is robust to disturbances and variations in operating scenarios, and its focus is on safety. All of the technical complexities, from the various aspects of mechanical, electrical, aerospace, and software engineering, are transparent to the user who interacts with Ignis through a simple and intuitive app for quickly and easily programming ignition missions. The app provides the critical real-time telemetry necessary for the UAV operator to monitor and modify missions in progress. The next video here is going to show some of the inner workings of Ignis and how it performs its functions. The hopper and dropper are secured below the UAV on the payload rails. The hopper is the upper portion that holds the ignition spheres, and the dropper is the mechanism below. The agitator moves a sphere into position above the loading chute in the hopper, and the sphere drops down to the dropper below. A hatch opens to allow the sphere to drop into the slipper block in the puncturing chamber. Once loaded, the sphere is forced onto the needle by the puncture motor and drivetrain. The hole of the side port needle is now inside the sphere wall, so it's ready for injection. The injection motor turns a lead screw, depressing the syringe, pumping antifreeze through the tube that connects to the back of the needle assembly. Once the sphere is injected, the bottom hatch opens, releasing the sphere to drop to the ground below, where it ignites 20 to 40 seconds later. This process repeats itself, alternating back and forth between side A and side B until the mission is complete. The next slide has a video that just details some higher level capabilities of the system. This video shows the autonomous aerial robotic system for fire management we have created at Drone Amplified called Ignis. It integrates with commercial UAS or drone platforms and is one of the most technologically advanced new tools for fire management professionals. Ignis is easy to use. The hopper attaches to the payload rails of the drone, and the main mechanism attaches to the hopper. It has a capacity of 150 ignition spheres, which are commercially available and already widely accepted. Once Ignis is loaded, it's ready for flights up to 30 minutes long. The system can deliver 30 spheres per minute to quickly ignite burn units. Once dropped from our innovative system, the spheres ignite the fire through a chemical reaction. Using our system to remotely distribute the ignition spheres keeps people safe at an affordable price point. The custom app we developed includes mission planning, programmed autonomy, telemetry, and safety features, and also captures significant data points for after-action reports. Through the tight integration of the mechanical, electrical, and software engineering, and with the help of feedback from fire management professionals, we have created the newest piece of safe, affordable, innovative fire management technology. So let's talk now about some more details of the capabilities. And hang on just a second, sorry. I apologize for the loud noise. I'm in my shop right now and my air compressor just kicked on. Sorry, capabilities of the system. So the Ignis uses the standard Primo fireballs, which are the 1¼ inch diameter ignition spheres, and then regular antifreeze. Has a pretty quick reload time for a single operator from touchdown to liftoff between missions can be about 5 to 8 minutes. It's lightweight, it's about 3.5 kilograms fully loaded. The wireless communication, communicates over the drone's command and control link, so your range should be around up to 5 kilometers. It has manual and programmable triggers, and you can actually pre-program trajectories and drop points for autonomous missions. And then it's delivered in the carry case you see there in the picture. So how much can we burn with this system? This is one of the most frequent questions we get asked. And the answer depends a little bit on the use case, but the chart here gives a few typical scenarios that range from burning 50 acres per hour for a pretty dense coverage with the spheres, up to 300 acres if you can drop more sparsely. And that depends on your fuel type, of course. The lower row gives an idea of the total area that can be burned in a day based on the number of hours operated. So if you burn for a full 8-hour day, you can burn quite a few acres with this. Move on now to safety. Safety was a significant consideration when we designed Ignis. There are over 15 hardware-based sensors that measure everything from motor position, motor rate, servo position, endpoint limits, current draw, voltage level, temperature, response rate, communication rate, and on and on. In addition to these hardware-based safety features, there are many more software checks running behind the scenes that ensure Ignis is functioning properly and is ready to get rid of a live ignition sphere as soon as it's injected. It also monitors just the overall operational status of the system as a whole. We've also developed a custom app that provides system-specific telemetry, as well as a live camera feed, and both these serve to increase operator situational awareness. The final line of defense in the event of an onboard fire is an emergency release mechanism that can be remotely triggered. The picture on the left, on the top, shows where an aircraft-grade steel cable attaches to the drone, and then it clips on to the Ignis dropper on the bottom. When the operator triggers the emergency release, the dropper disconnects from the hopper and hangs from the tethers at a safe distance while the jammed ignition sphere burns itself out, essentially. You can see this configuration over here on the right. This helps to mitigate the risk of damaging the rest of the system, and it prevents the propagation of fire to the rest of the drone. I'm going to talk about the user interface now, which is the app, essentially, we've created. So this is the home screen of the app we developed. There are a few different submenus from here that allow the operator to download maps and map overlays, and also access the main flight interface. So the ability to download those offline maps I just mentioned is a critical feature that makes our app especially useful for land and fire managers, because internet access is often pretty limited when you're out on site. So our app allows operators to access the maps they need while they're at home or the office and they have internet access. So they download those high-resolution satellite images by just pinching and zooming around on the map interface and then clicking download, rather. You can see all the regions you have downloaded on your tablet, and these satellite images automatically populate on the global map within the flight app. Along with the offline maps we just talked about, the Ignis app supports geo-referenced PDFs and KML shapefiles as overlays on the satellite imagery. So for example, you can download the day's most recent IR map from, say the NIFC FTP site or similar source, whatever you use, and then you can overlay this on your satellite imagery. The picture on the right shows what this looks like in the app. The UAV position is shown real time during flight over top of that IR map. So the operator can correlate the current fire line with the IR map data from the previous day, or they can ensure they stay within the boundary of the fire line. Terrain data is also automatically downloaded for regions saved to the offline maps in the app. The picture on the left shows the app screen displaying a color-graded topographic representation of the landscape. You can also see the drone altitude and the home waypoint altitude. And then the terrain data can also be used when you're planning mission trajectories. The app screen on the right shows waypoints being placed to follow the contours of the landscape. This allows for dropping spheres from a consistent height while also maintaining a safe distance above elevation changes in the landscape. Now, there's a lot going on in this screen that shows an ignition mission in progress, so I'll just walk through what each of the icons and the graphics mean. The white polygon here surrounding the area is a geofence that's uploaded to the UAV so that if it flies outside this area, it's going to stop dropping spheres automatically. This ensures that fire's only dropped where you intend to. Adding a geofence is as easy as just touching 3 or more points on the map to make a polygon surrounding the burn area. The blue and yellow icons are waypoints that are added by touching points on the map. They're selectable as either start dropping or stop dropping points. The yellow lines indicate drop lines, and the blue lines are transit lines. The operator, so you just select these lines, select whether you want them to be dropping lines or transit lines, hit the auto takeoff button, and start. And the UAV takes off and flies the pre-programmed mission and returns home when finished. The pink and white spheres trailing the UAV icon show where ignition spheres are dropped, and they remain visible from mission to mission, so if you stopped partway through, you can pick up right where you leave off on the next mission. There are a few camera options. Is my audio back? Can you hear me again? Okay, sorry. There are a couple camera options. Visible and IR are the two general categories. The visible spectrum on the left and the IR cameras on the right. And either of these video feeds can be displayed through the live feed in the app. The visible cameras are less expensive and they provide excellent situational awareness and an overhead perspective for analyzing the fire. But the one downside to them is, as you can see now, they get pretty obscured in heavy smoke or at night, obviously. And that's where the IR, the thermal camera, really shines. The video on the right was shot at night out in Oregon this summer on one of the wildfires. And one of the lessons that was learned out there is that Ignis, coupled with a thermal camera, fills an incredibly useful role because it can fly at night or during inversions when manned aircraft are grounded. And so Ignis was used to continue ignition operations at night to help set up for the day crew coming in the next morning, and it reportedly made for a very efficient workflow. So that is the end of the presentation portion I had today. Hopefully there are a few questions here that we have time to answer.
Yeah, thank you. That was a great presentation. Really nice to kind of get into the details, because I've sort of heard about these things, and now I have a much better sense of how they actually work. So the first presentation comes in from Pete, and he's asking about how you compensate for steady or gusty winds. Yeah, so the UAVs have developed quite a bit over the last 5 to 7 years. They're quite stable. Here in Nebraska, wind is an everyday occurrence, so we commonly fly in 25-mile-an-hour winds. So certainly you can fly in much windier than you want to do a prescribed fire in, and I would say you can still fly on even up to some of the windier days on a wildfire. They're very, very stable. Great. And then another question came in about mounting multiple cameras. Could you choose to have both infrared and visible? Yes, so actually the thermal video you saw in the presentation is actually a dual, it has a visible spectrum camera and a thermal spectrum camera on the same. And in our app, you just select whether you want to see the thermal image or the visible image or both at the same time. So the answer is yes to all. Okay, great. I could see them both being useful in slightly different situations. Mm-hmm. Let's see. Nathan asks about compatibility with other drone sort of bodies, the basic drone vehicles, UAV vehicles. Is the Ignis system sort of custom made for the DJI, or could it be compatible with other UAVs?
Yes, it is. We have integrated with other commercial systems. For better or worse, the M600 Pro right now is the best combination of flight time, stability, and price. The other vehicle we integrated with was about 3 times the cost, flew for 1/3 of the time, and was not very stable. So, you know, value-wise, the M600 is your best bet right now. That being said, we can easily pivot and put it on other things. I mean, we rewrite all the software and stuff ourselves, so we can integrate with other stuff. If your agency has something you already use, we're more than happy to roll with that.
And I'll just note, I guess it was last month, we had another presentation through the same webinar series, again on UAVs, and there was a whole discussion about DJI and the ability of the federal government to use that platform. And I think there's some sort of pending changes there or progress there in terms of, I guess the issue is connection with servers outside the country. So maybe we don't need to get into that now. I just want to acknowledge that that's been come up before, and maybe I can share a link to the past webinar as well, because folks might be interested in that.
Sure, yeah.
And then a couple more questions here. Oh, I guess I should recognize we are at the top of the hour, so I certainly understand if you have to log off. We really appreciate all the participants joining today. I think we'll probably run over just a couple minutes to try to answer a few more questions. But obviously, if you got to go, that's fine. So Michael asked about a price tag. What does a system like this cost? And it's probably, there's probably a whole conversation around price, but if you can talk about sort of ballpark numbers to give people a sense of where
Sure.
in that schema.
Yeah, absolutely. So the Ignis payload is going to be in the $15,000–$16,000 range because there are sort of a range of configurations you can do. But that will get you an Ignis payload. The M600, which is a DJI product, is $5,000. You know, if you want multiple sets of batteries, the battery sets range from $800 to $1,200. So just for an example, we sold sort of a complete package to a contract group who basically went from having no drone anything to having a fully functional package they're burning with on a daily basis, and it would cost them about $25,000. So if that gives you a ballpark estimate. You know, it'll depend on you, what you already have, what you need, etc. But hopefully that gives you an idea.
Yeah, no, that's really helpful just to kind of put some numbers on it. Yeah. And then Jeremy asked about delivery of the thermal maps. So are those available on Firefly?
Yes. Basically, the NIFC FTP site is the federal sort of repository, I believe, for IR maps. So any incident that they are on where they have daily IR maps, you can get those from there. I know that a lot of people use like Avenza, and so anything you can use in Avenza. I don't know where all people pull their information from, but you can pull it from there.
Okay. And then Paul was asking about safe return to launch point if there are problems or contact is lost or, you know, something doesn't go as planned. Is that sort of
Sure.
for the system?
Yes. Yeah. So it's a pre-programmed basically response. So before you take off, you would set your behavior. If your battery runs too low or if you lose connection, you would say, you know, come home at 100 meters height, or, you know, whatever a safe height is for your location. You would pre-program that, and it would come home when it's done.
Okay. And then Craig asks about the flight control. Are there options to use other flight control software, or does it need to be the Ignis software because of the dropper integration?
Right. There's no other software out there right now that will run, the ignition processes. There are many apps for flying UAVs, but if you want to do ignitions with Ignis, you need to use our app. Yes.
Yeah. Okay. And just to clarify, Jeremy was asking about the georeferencing, and so all the flight paths and the drops are all georeferenced, right?
Yes, that's correct.
Okay. So sort of following up, or looking a little out of order, I should have found this question sooner, but back to the issue of wind. So is it possible to do any adjustments for a wind effect on the spheres as they drop? I guess the idea being, if you're going in some heavy winds like you guys have in Nebraska, do you plan drops differently so that the balls, move as they drop?
Yeah, that would sort of be a pre-planning thing. So as you're programming your mission, if you have a very strong east wind, you'd want to fly a little bit to the west of where, you wanted them to drop. It is not doing any in-flight calculation. Wind is a very challenging thing to measure, especially from a rotor wing vehicle that's creating significant wind itself. So we haven't tried to tackle that technical challenge yet. So yes, you just sort of need to adjust your flight path based on what you feel the conditions are. Okay.
Let's see. We have a bunch of questions here. And I'm going to try to pick out some ones we haven't necessarily talked about. I guess one, I think this is coming from a Canadian colleague. Do you want to talk at all, Jim, about the sort of restrictions or interactions in terms of regulatory constraints on doing aerial ignitions?
Yes, so I see that Brad Keckeritz just weighed in a little bit. There are significant regulations here. Some agencies have their own agreements. So in the States, at least, I should talk. I'm not as familiar with Canadian policy, but in the States, certain agencies have agreements with the FAA that allow them to do certain things. For us, as a drone amplified, as a private company, we had to go through a couple different processes, basically getting waivers for certain regulations that the FAA has put forth to allow us to drop incendiary devices. And I would let Brad or Steve, some of the guys from the OAS group, weigh in on what all agreements they have. But they are allowed to do some things that we are not allowed to do, just because as part of the federal government, they're tied in a little closer and have prearranged agreements. In Canada, I don't want to weigh in because I'm not nearly as familiar, but I would certainly imagine there are some analogous regulations that you would have to work through.
Yeah, no, that all makes sense, and obviously. Certainly the consortium is not advocating people run, get a drone and start, there are paths that follow on these things. But I think our motivation here for inviting the presentation was really like, this is a change in technology. And I know, thinking about trying to get good fire on the ground in the Southwest, there are some barriers that this could overcome, and that's the sort of context. I think it's really important to think about, hey, are there burn units or opportunities that we're missing that we could, if we follow the right approval process, etc., could we address them with these sorts of systems? But I think it's important to highlight that, yes, there are rules here.
Yes, absolutely.
Let's see. Yeah, and someone actually suggests a policy webinar, and thank you, Bradley. That could be really useful. Clearly, there's some interest in UAVs, and maybe I'll follow up with you, Bradley, and sort of think about how the best way to do that. Maybe I'll pick out one or two more questions here, and then we'll sort of wrap up. David was asking, you sort of talked a little bit about purchase price, Jim.
Mm-hmm.
You guys have any kind of estimates? Obviously depends on how many balls you're dropping per minute or acre, but sort of an hourly cost of operation. And I guess I often hear helicopter hourly costs, and so maybe that's the kind of comparison we're hoping for.
Right. You know, it is an electric powered vehicle, so you know, your electricity rates vary upon region. If you're running a generator, you know, your consumable cost is pretty low. Antifreeze is cheap. The spheres are a little bit more expensive, but you know, I would say there's probably an annual. You'd have to break down the annual maintenance cost into the hours per year you use. So I guess in short, I don't have a great answer for you because it does depend a little bit on you. You know, the batteries, the batteries you should expect, if you take good care of the batteries, you should get at least, you know, at least 400 charge cycles out of those. I'd say closer to 500 or 600. So I mean, it's fairly low, I would say, comparatively to many other tools you'll find.
Yeah, and I would hazard that things like staffing costs, like if you capitalize, like if you capitalize the purchase costs, then a lot of your operational hourly costs are going to be things like staffing.
Yeah, agreed.
Definitely good conversation, important question. Chad asks about, have you guys considered modifying the firing mechanism for the 26 millimeter Dragon egg spheres?
Yes. So we originally went with the fireballs, the 32 millimeter ones, because most of the people we talked to already used those for their helicopter ignitions. So they said, oh yeah, we got 10 boxes of those in the shop right now. So that lowered the entry bar for us a little bit by using what most people were already familiar with. But we are actually currently working on a design for the smaller Dragon eggs to basically increase capacity.
Great. And then maybe our last question here, Christine is asking about smoke monitors and you know, whether you guys have thought about or whether it might be possible to attach a smoke monitor, particulate matter meter, so you could measure that during ignitions as well.
I would say probably. I'm not super familiar with smoke monitor technology, but you know, if it's a fairly small light sensor, it seems like that would be decently easy to integrate. The only thing I could think of is that you know, rotor wing aircraft create a fairly significant downward breeze. So if you need real still air, you might have a little bit of a hard time finding that in the very close vicinity to the props. But if that's something that's really useful, I'm certain we could figure something out.
Yeah, no, it's an interesting idea. I know we've been thinking a little bit about smoke monitoring because that's often a real hassle with prescribed fire, making sure that we're not impacting people's health. So
okay, actually, I just I got a text from one of the OAS guys who said they did it with volcano particulate matter in Hawaii. So yes,
there we go.
Can do it.
Cool. All right. Well, there we go. All kinds of new topics here cropping up. Well, I want to respect everybody's time. Jim, I really want to thank you. Patrick, thanks again to you for your presentation. I know it was a little bit, there's a lot of information today, and which is why we went over, but I think it's fun to kind of combine these two uses for UAVs in one presentation. So thanks everybody for sticking around and listening, and I hope you'll join us on future webinars. So thanks everybody very much.
Thank you.